Hi everyone, welcome back. And so for this video, we will be learning in order how to solve for first order exact differential equation. This is our very first example for an exact differential equation. So we do know that we have 2x minus 1 times dx plus 7y plus 6 times dy. And this is indeed in the form of an exact differential equation. And our very first step to solve this exact differential equation is to check whether it is an exact or non-exact. And how to check it? First, we know that our m here is equals to 2x minus 1, and our n here is equals to 7y plus 6. And so, let's take the partial derivative of f with respect to y here, which this gives us 0. And let's take the partial derivative of f with respect to x here, and this will also give us 0. And then we can draw our very first conclusion, which is my equals to nx. And therefore, this is exact or an exact differential equation. And so we can solve it. First, we know that this is the partial derivative of f with respect to x, and this is the partial derivative of f with respect to y. And I'm gonna use this equation here, which is fx equals to 2x minus 1, and let's integrate it, equals to the integration of 2x minus 1 dx, and this integration will give us x squared minus x plus hy. You can call this hy, gy, by, cy, but this is just a generic function of y. And then we're gonna take the partial derivative of f here with respect to y now, which f of y equals to 0 minus 0 plus the derivative of h, and this simply gives us the derivative of hy. And after this step, we're gonna do our last step in order to find us our hy component here, which we're gonna use this partial derivative of f with respect to y and make it equals with hx and y, which we're gonna do it right here, equals to 7y plus 6, and we're doing the same thing. We're gonna integrate it as well. So h of y equals to the integration of 7y plus 6 dy, and this integration gives us 7 over 2 y squared plus 6y plus c. Don't forget the constant here, because when you're integrating something without bounds, there should be a constant. And so we have here, we just need to we have here our h of y, and we just need to plug it in back here. And that will be our final answer to this exact differential equation. So x squared minus x plus 7 over 2 y squared plus 6y equals to c. It should be a plus c here, but if I minus or subtract both sides by c, the left side should be negative c, but negative or anything times a constant will still be a constant. So this is our final answer for this first example of an exact differential equation. Everyone, we are back with our second example for an exact differential equation. What we have here is that we have x plus y squared times dx plus 2x times y plus x squared minus 6 times dy equals to 0, and we have an initial value problem of y1 equals to 1. And first, our very first step, remember, we need to prove this whether this is an exact or non-exact differential equation. And let's start by defining our variables here, which is mxy, and I would like to expand the one that's in the bracket, becoming x squared plus 2xy plus y squared, and our n xy here will become 2xy plus x squared minus 6. And let's take the partial derivative of f with respect to y here, which our x's are the constants, which this will be 2x plus 2y. And let's take the partial derivative of f with respect to x here. That means our y are the constants. This will give us 2y plus 2x. And we can draw our first conclusion, which is my equals to nx. Therefore, this is an exact differential equation, and we can solve for it. And so, like the previous example, I'm going to take this partial derivative of f with respect to x here, and later on integrate it. And so, f of x equals to x squared, after we expand, plus 2xy plus y squared, and we're going to integrate it, which is fxy equals to the integration of x squared plus 2xy plus y squared dx. Remember, in this integration process, what are our constants? Our constants are the y's. So x squared will become 1 over 3 x cubed plus 2xy will become x squared times y squared will become x times y squared plus h of y. You can put it gy, by, ay, anything, but this just represents the generic function of y. And so let's take the partial derivative of what we've got here with respect to y. And so this is 0, this is x squared, this is 2xy, and hy will be hx and y. And after taking the partial derivative of y of f with respect to y here, let's set it equal with our partial derivative of f with respect to y here, because they are both equal to each other since they're the partial derivatives of f with respect to y. And we can solve for the hx and y to find the hy later on, equals to 2xy plus x squared minus 6. And here, let's cross out all of the variables that we can cross out with each other, which is the 2xy as well as the x squared, and this just leaves us with the derivative of h equals to negative 6. And we want to integrate it to find the hy in order to substitute it back in the original equation. Negative 6 times dy, and this integration gives us negative 6y plus c. And from here on, we can substitute it back here to this equation here that we've got after we integrated the partial derivative of f with respect to x. And so 1 over third x to the third plus x squared times y plus x times y squared plus actually minus 6y equals to c. Okay, so this is the general solution for this differential equation. But we've been given at the start of the problem an initial value condition or initial value problem, which is y1 equals to 1. And that we need to find c or solve for c. And so let's plug in 1 into the y's and plugging also 1 into the x's. 1 over third times 1 is 1 over third plus 1 times 1 is 1 plus 1 times 1 is also 1 minus 6 times 1 is 6 equals to c. And 1 over third plus 1 minus 6 will just gives us negative 11 over 3. Negative 11 over 3. And after we've got the c value here, or the constant here, let's just plug it back here. And this will give us our final solution, which is 1 over third x to the third power plus x squared times y plus x times y squared minus 6y equals to negative 11 over 3, which is our constant that we found after plugging in it the initial value condition. And so this is how you solve for an initial value problem for the exact differential equation. We are back with our third example of an exact differential equation. So without further ado, let's go and solve the problem. We've got here y squared times cosine x minus 3x squared times y minus 4x dx plus 2y times sine of x minus x cubed plus ln y times dy equals to 0, and we've got an initial condition or initial value problem of y0 equals to e. So first, we know that this is all mxy, and all of these are nxy. And our very first step will still be the same, proving whether this is an exact or non-exact differential equation. And so let's take the partial derivative of f with respect to y here, which x's are the constant and the y are the not non-constant ones. And so my equals to 2y cosine of x minus, remember the x's are the constant here, 3x squared. And let's take the partial derivative of f with respect to x here. This will become 2y cosine of x minus 2x squared, actually 3x squared. And then we can draw our first conclusion, which is my equals to nx. Therefore, we've proven that this is an exact differential equation, and we can solve for it. Moving on to our next step, we're gonna take this, which is the partial derivative of f with respect to x, f of x, xy equals to y squared cosine of x minus 3x squared times y minus 4x, and we're gonna take the integration of it with respect to x, of course. The integration of y squared cosine of x minus 3x squared times y minus 4x dx. And remember, in this integration process, our constants are the y's. So we need to integrate it towards the axis. And this will give us y squared sine of x minus the integration of 3x squared times y is x cubed times y. 4x is just 2x squared plus hy, or the generic function of y. After we've done with this step, we're going to take the partial derivative of f with respect to y, which this becomes 2y times sine of x minus x cubed plus hxn of y, or the derivative of h. And afterwards, we're going to set it equals to the partial derivative of f with respect to y here as well, which this becomes 2y sine of x minus x cubed plus hx and y equals to 2y sine of x minus x cubed plus ln y. And let's cross out all of the variables that we can cross cancel with each other, which are the 2y sine of x as well as the negative x cubed, and this leaves us with hx and y equals to ln y. And we're gonna take the integration of ln y dy, and for this integration process, for the sake of the video, we're gonna do it step by step, but we all know we will be using integration by parts, which is u phi minus phi du. And let's see, our u will be ln y, our du, or the derivative of ln y, will be 1 over y dy. Our integration of phi will be 1, and our phi will be y. And so let's substitute it back in this u times u and phi du, which u is ln y, phi is y, so that's just y times ln y minus the integration of phi, which is y, times du, which is 1 over y dy, and this will just gives us ln y, or y times ln y minus y. And so our h of y is equals to y ln y minus y. And so let's substitute our h of y function here, which then will gives us y squared times sine of x minus x cubed times y minus 2x squared plus y ln y minus y. And don't forget to add the constant here, since this will equals to c. This is not the final answer, because remember, we've been given at the start of the problem an initial value condition, which is y0 equals to e. And let's solve for c and substitute it back in there. Okay, so we know that the x's are 0 and the y's are e. So this will be e squared times sine of 0 minus this is 0 times e minus this is 2 times 0 times 0 plus e times ln e minus e equals to c. And we know that this will equal to 0 minus 0 as well as minus 0 plus e times ln e. Remember that ln e is equals to 1, which this is 1, so e times 1 minus e equals to c. And here we can see that C is equal to 0. And by then, this is our final answer for this exact differential equation. Minus x cubed times y minus 2x squared plus y ln y minus y is equals to 0. And this is our final answer to our exact differential equation as a particular solution, since an initial value condition was given at the start of a problem.